So, beginning with the basic equation in Schrodinger picture, which is our familiar Schrodinger equation. This is state gate psi at time t in Schrodinger picture, which can be obtained by the operation of this time evolution operator on the state gate at time t equal to 0. And if we make this gate notation as bra notation, this right hand side will look like this, and this is discussed. I have already used this relation in part 1 of this time evolution series. Now we are going to write the expectation value of the operator O in the state psi t, and this operator is in Schrodinger picture. So I have written S here, and this operator OS is sandwiched between the two state gates psi t and psi t. Both are in Schrodinger pictures, which is quite obvious. So instead, in place of psi t, I have used this relation, and in place of instead of this psi t bra, I have used this relation, and finally I have obtained this from this. So this is how the expectation value of the operator will look like in Schrodinger picture. Besides this Schrodinger picture, we have another picture which is called the Heisenberg picture. This is an alternative approach, and in alternative approach when applied to time evolution. In Schrodinger pictures, the operators corresponding to observables like position, momentum, spin, they are fixed in time. Actually, the position means x, and momentum, by momentum I mean py or pz, or by spin I mean the sz, that is the z component of the spin, to be precise. They are fixed in time, while the state gates vary with time. But in contrast, in the Heisenberg picture, the operators corresponding to observables vary with time. But the state gates, they are fixed, they are frozen they were at some initial time t0, and for convenience we take t0 equal to 0. So the time evolution operator looks like this, and that is defined by this equation. In Heisenberg picture, the observables are defined like this, where this S stands for Schrodinger picture and H stands for Heisenberg picture. But one thing I would like to mention, that initially, that is at time t equal to 0, the Heisenberg picture observable and the corresponding Schrodinger picture observable, they coincide. That means if I write a H at t equal to 0, this is same as a S at t equal to 0. This is what I mean to say. Now in Heisenberg picture, the state gates, the state vectors do not evolve in time. So psi t is the same as psi 0 in Heisenberg picture, and that is also equivalent to psi 0 in Schrodinger picture. So initially the state gates in both Heisenberg and in Schrodinger picture, they also coincide. So at t equal to 0, the state vectors are same in both the pictures, but as time evolve, in Heisenberg picture, these state gates are like frozen, and in Schrodinger pictures, the state gates vary. So initially the state states are same in both Schrodinger and Heisenberg picture, but the physically observable quantities, they depend on time, because if we want to measure position of a particle, if we just forget about quantum mechanics, if we think about a classical particle, if we just roll a ball, so at time progress its position changes. So the observable quantities, they depend on time. So in Heisenberg picture, the observable quantities which are represented by the operators, which means this operator correspond to several of the observable, several measurable quantities like position, momentum, etc., spin, etc. So this is how these operators evolve in time in Heisenberg picture. And I have mentioned earlier that initially, that is at t equal to 0, the operators are the same in both Heisenberg and Schrodinger picture. This is to show you that the expectation values are picture independent. So let me write the expectation value for the operator O. This is the standard definition. As the operators O are written in Heisenberg picture, so they are time dependent. So this T is here. This reminds me that this operator is time dependent, and state states are written like this. By keeping in mind this relation of the operator, this is how we defined the observables in Heisenberg picture. This is the value of the operator at t equal to 0, and we know at t equal to 0, that is initially, the value of the operator for Schrodinger picture and value of the operator for Heisenberg picture, they are the same. So here I have used that relation, and for t equal to 0, the operator is this one. So when I am writing this time evolution operator operating on this, and the time evolution operator is there operating on psi 0, and as psi 0, they are same for both Heisenberg and Schrodinger picture. So in place of psi 0 h, I can safely write psi 0 s ket, and for psi 0 bra h, I can safely write psi 0 s. And as at t equal to 0, OH, that is operator in the Heisenberg picture, is equal to operator in the Schrodinger picture. So I have also replaced OH with OS, and this is by definition psi t, as we have just discussed. So the expectation value of the operator in the Heisenberg picture, which was this one, is the same as the expectation value of the operator in the Schrodinger picture, which is quite obvious, because expectation value is something which gives us physical meaning, which gives us value of some real observables.